Hello, in this video we're going to go through the work energy principle and how we use it. In previous videos we've talked about work and energy, and we started from the basis that work is force times distance, which if the force is varying across the distance is the integral of force with respect to distance. Let's link that up with Newton's second law, F equals ma, which we also know that A equals dV by dt. Now if we integrate Newton's second law with respect to x, on the left hand side we get F integral dx, which we know is the work. On the right hand side we've got m dv by dt integrated dx. Now we're going to do something here, we're going to swap these two over, and that's a legitimate thing to do because when we're looking at the infinitesimals. And what does that have the effect of? Well, here we've now got dx by dt, which we know to be v. So what we've actually got here is the integral of mv dv, so integral of momentum dv. And if we integrated that, the integral of v dv is v squared over 2, isn't it? So the integral of that integral is a half mv squared. I've also put square brackets around that because we're interested, if we did that integral, be the change in that value. So on the left hand side I've got work done, and on the right hand side I've got the change in, and this we're going to call kinetic energy. Yep, this is the energy actually absorbed in motion. You probably come across it in physics at GCSE, but that's kinetic energy, and that's where it comes from. It comes from this work energy principle. So there we go. How can we use that then? Let's have a look at a couple of examples that we used earlier. Here's the one where we're moving a 10 kilogram mass. I apply a 20 Newton force to it, and I let that force apply to it for 3 meters. And therefore the work done is force times distance, 20 times 3 is 60 joules, yeah? So we now know the work done. And that's going to be the change in kinetic energy. So if this body was still at start, it was at rest, it's going to start be moving at the end. Yeah, there's the work energy principle written out in maths. We know that therefore the kinetic energy afterwards is going to be the work done, which will be 60 joules. Yeah, if we started from no motion at all at rest, there was no kinetic energy. So there's half mv squared will equal 60. Substituting in that the mass is 10 kilograms, I've got 5v squared on the left. Divide 3 by 5 and then square root it, and we get that the velocity at the end is 3.46 meters per second. We can do a very similar thing with our satellite falling to Earth example with a extremely complex universal gravitational law force. Yeah, so let's see what happens if we allow this satellite to drop from 200 kilometers down to the Earth. Yeah, so it's going to drop down. It's going to, as if it's starting from 0 speed. Yeah, and it's going to come down. I'm going to assume it's a 400 kilo satellite. We in the last video we proved that if we integrated the above, that the work done would be GMM, and bracket here being the difference in the reciprocals in the radius, how high we were. Here are the values that are standard, so using this equation, and I'll leave this on the screen just a sec, so that if you want to you can stop and have a look at the calculation. But the work done by gravity here is 6.97 times 10 to the 8 joules. That's an enormous amount of work, isn't it? That's work that's actually pulling this satellite down to Earth. And if there were no air resistance, it was just being pulled down by gravity, all of that work would be converted into kinetic energy. So the kinetic energy, half mv squared, is going to be the 6.97 times 10 to the 8. Putting in the mass there and then dividing through, we find that the velocity at the end is nearly 2,000 meters a second. That would be a hell of a crash, wouldn't it, if it hit the Earth? Okay. The other thing that's really useful about the work energy principle is we can use it to think about our potential energy. So let's have a look at this example here. I've got a body here, this body, and I'm going to lift it up from height 1 to height 2 using this blue force F. Yeah. So the actual forces operating on this body, we've got a resultant force upwards, haven't we, of F minus mg. Yeah. And we're going to lift it up, and it's going to be at rest at the end. So I move it from here to here, that height to that height. We can see, therefore, at the end, if it's at rest, there is no kinetic energy, yeah, because V equals 0. So the right-hand side of our work energy principle is 0. What happened on the left-hand side? Well, the force acting on our body was F minus mg, yeah, and we integrated it dx and over the full height, yeah. So we can rearrange this, and that lot's going to be equal to 0, as I said, because it's static at the end. And if we can rearrange this equation to put the blue force on one side and the gravity on the other side, so what we're saying is that the work done by F is entirely against gravity, and it must be of the same value of the potential energy. So if we integrate this, the left-hand side, well, we know that's the work done. On the right-hand side, I've got mg dx, and therefore once you've integrated it, I've got mg and h2 minus h1. Now this has quite an important point here, is that this shows us that gravity is a conservative force, because the amount of work against the gravity doesn't say anything about the root. It only has two values in this equation on the right. It's got h2, our final position, and h1, our starting position. There's nothing there about how we got there. We could go any route we like from h1 to h2, yeah. We go up, and then we can come down, yeah. The only things that are important are h1 and h2. So this is a conservative force, and we know that, don't we? We can lift something up and it will stay there. When we take it down, it releases energy to us, it pushes us down, yeah. So if a body is lifted up, we store gravitational potential energy. What we've seen above is that gravitational potential energy is mg and the change in h, but quite a lot of the time people write gravitational potential energy as just being mg and mgh, yeah. So that's proved our gravitational potential energy. We can do the same thing here with elastic potential energy. So here I've got the end of a spring, I've got a body on the end of a spring, and I lift it up using force F. So we're battling against the spring, which under under Hooke's law, we know that the force of the spring is going to be kx, where x is the extension of the spring. So let's extend the spring from x1 to x2. And again, at the end of it, we're just going to hold it still. So there's going to be no kinetic energy on the right-hand side of our work energy principle. So what we've got to do is look at the left-hand side. And the left-hand side, we know that the force being applied to the body here is F minus kx, yeah. And again, that's the work done is going to be 0. So if we do the split as we did before and put the integral of f dx on the left hand side, then on the right hand side we've got the integral of kx dx, and there we go. If we look at that, we integrate kx, we're going to get a half kx squared, aren't we? And therefore the work done here is going to be a half kx squared of final position minus x squared of initial position. And again, that's showing us that elasticity is a conservative force. There's no other terms in here, which just only matters about what the final position is and the initial position. And we know that that all fits together, doesn't it? Because we want energy to be stored in our spring. That makes sense, doesn't it? If we either stretch our spring or we compress our spring, we're storing energy in it. Yeah, that's an interesting point, isn't it? Because it's x squared. Doesn't matter whether we're squeezing it or stretching it, we're still storing energy in it. So elastic potential energy, looking above, we could think of it as being the differences here, but most people will be thinking, when you say what's elastic potential energy, they're going to say to you half k x squared. Okay, there we are then, this video. Work energy principle, we've looked at, we've proved it, and it tells us that the work done by forces going to result in a change in kinetic energy. And we use that to prove that the potential energy, if that force was gravity, was mgh, and if it's elasticity, it's a half k x squared. So there you go.